In this video, I will be evaluating the integral from 0 until 2 pi of 1 over 5 plus 4 sine of x dx. Right? Okay, so let's first start off by noting that sine of x is e to the I x minus e to the negative I x over 2I. Right? So we can use this to our advantage by making z equal e to the ix, and dz is then going to be I e to the ix dx, right? And now I can replace this formula by e to the ix is z, e to the negative ix is z to the negative 1. I can replace e to the ix in this by z, right? And then I get dx equals dz over iz. And I can imagine plugging this in, but I have to figure out my bounds of integration. I know what my bounds of integration are going to be, because they're going to be the unit circle. How do I know that? I have e to the ix, and x is ranging from 0 to 2 pi, and that just gives me the unit circle, right? Given any angle theta, e to the I theta will be on the unit circle, and because we're giving theta between 0 and 2 pi, that will give me all the values, okay? So that I'll call that curve C. So this is going to be the integral over C. I'll write a little circle through the integral of, let's plug in all my values. Dx is going to be dz over iz. 5 plus 4 sine of x is z minus z to the negative 1 over 2I. Right? Okay, so now we have the integral along the curve C. I'm going to multiply the denominator and the numerator by iz. So that'll cancel out, and I'll get 5iz plus 4, 2, so I have a 2 there, right? Multiply it by iz, so 2I z times, and then z minus z to the negative 1 over I. Okay? And you may notice those i's cancel out, and so we're left with this. Okay, so this gives us the integral along C of dz over 5iz plus, multiply by 2z all the way through, 2z squared minus 2. Okay? I'm going to rewrite that denominator a little bit so that it's in standard form. I get 2z squared plus 5iz minus 2. Okay? So now, how do I figure out the poles of this? How do I figure out all the singularities? Well, let's figure out when the denominator is 0, right? So the denominator is going to be 0 when z equals negative 5 plus or minus, using the quadratic formula, negative 5 plus or minus the square root of b squared minus 4ac, which will be this, okay? Okay, and you'll get out negative I over 2 and negative 2I, okay? Now, what the residue theorem says is that if I evaluate each of a very specific formula and I multiply it by 2 pi I, then I will get the original integral. But it only applies to these poles which are inside of the interval. So right there's going to be negative I over 2. Right there's going to be negative 2I, right, on the circle. Only negative I over 2 is going to be in the circle, so that's the only one we care about. So let's evaluate the residue is what it's called, of this at negative I over 2. And what you do is you do the limit as z approaches negative I over 2 of z minus negative I over 2. And you're going to multiply that by your original function, which we know the roots of this, so we can actually write it as 2z plus I over 2 and z plus 2I, because we know the roots, right? Oh, but look at those. Those are the same. I can cancel them out. Now I can plug in for z equals negative I over 2, which gives us 1 over negative I over 2 plus 2I, which is going to be 1 over 3 halves I, which is going to be 2 over 3I, right? And now what the residue theorem says is that I can multiply this by 2 pi I, that by 2 pi I, right? So I get 4, those i's cancel out, 4 pi over 3. And that's it. That's our answer. That's what the residue theorem says. That evaluates this integral right here. But because we made a substitution and we found out what we were integrating over, it's also going to be that integral. So it's 4 pi over 3.